continue working with TopCat because, like he told you, two of the most powerful tools with Virtual Observatory is TopCat and what did you say? Aladdin. But if you actually see the VO page, please have a look at this. You can always find this page, International Virtual Observatory Alliance, right? Google it for it, you'll be able to find it. I can show it to you. If you just Google VO tools or you Google IVOA, that is the International Virtual Observatory Alliance. The first hit that you get is ivoa.net. Okay, this is the website for International Virtual Observatory Alliance. If you click on For Astronomers, go on For Astronomers, then you will see various things getting started using the VO glossary, VO software, etc. If you go through the VO software, you will see there's a whole bunch of software. So you obviously see that we cannot in one day cover all these softwares, right? Because there are many softwares depending on what you want to use it for, right? So for example, image visualization, there's Aladdin, there's Skyview, there's Firefly. You've already seen ESA Sky, which is not mentioned over here, but Aladdin is also another one, which we will also show that to you. Similarly, for other functions, there are many more things. We are not going to cover all these things, obviously, but depending upon your requirement, we will do it. But we'll continue focusing on TopCat and Aladdin. Many of these other things are similar with a certain amount of these things. For example, spectral data, there is something called VUSA as well as VOZ to handle spectral data. And then there are many different other things. So let's go back to our TopCat page. If you go back to the TopCat page, you will find this page for downloads. And like I told you, if you have a Mac, you will have to download the DMG file, which is topcat.all.dmg. Otherwise, you will have to download this one, topcatfull.jar. So you just double click it. It will tell you to save it wherever you have. And wherever you save that file, you just have to run the command. If it's a Linux machine, you just have to run the command java -jar topcat, the file name .jar. If you're using a Windows system, you'll just have to double click this jar file, and with that you will open TopCat. Okay, so if I show you what TopCat looks like, I will share my whole screen, and you will see that TopCat looks like the cartoon character TopCat, and it opens up like this, right? So I hope you can see it. Okay, wow, you can see it. So this is the TopCat screen, which you've already seen with Alexandra. He showed it to you. And now we are going to show you how we can use TopCat to actually even access Gaia data, right? Because he made it easier for me by actually talking about Gaia data, which is my favorite data set, which is what I like to work with the most, right? So what you can do with TopCat, he showed you, but what we're going to show you is how can you, for example, plot an HR diagram of a star cluster, or in principle even get the distance to a star cluster, right? So what is a star cluster? Is nothing but a group of stars which are born from the same molecular cloud. So they are at the same distance, they are moving with the same velocity, and they have the same chemical composition, right? So Gaia actually gives us the set of data which we need, which is parallax, which is distance, and proper motion and RA, proper motion and tech, right? So let us go to one of the most well-studied star clusters. I'm sure you all know this cluster very well. It's called Pleiades. Pleiades is the Seven Sisters or Kritika, or it is M45, okay? So one way of accessing VO data from TopCat, one way is what he showed you, but I'm going to show you another thing. TopCat also has a switch over here called VO. So if you just click on VO, you can say, I want to do a cone search. And in the cone search, you can say your keywords are Gaia and say you want DR3. So when you say I want Gaia DR3, you say find services. So it shows you all the sources where Gaia 3 data is sitting, right? So this is the EDR3, that is the early data release 3. So be careful, don't choose that. Choose the other one which has DR3. Okay, there's a difference between the two. So here I'll say my object name is M45, that is Pleiades. Now to see how well this is embedded. When I say M45 and I say resolve, what it actually does is it goes to Simbad, okay? It queries Simbad, and from Simbad it gets this RA and DEC. That means it gets the positions of the cluster Pleiades from Simbad by pressing resolve. Okay. Now it wants to know what is the radius or the size of the data which I want to. Now we should not go in degrees because degrees are very large, and basically Gaia gets like a billion stars. So if you choose like a few degrees, you won't be able to, manage much. So let's say we take, or even if I take 1 degree, let me say, okay, if I say 60 arc minutes, 1 degree, I can query it, but I'm following at the risk of it's going to take some time to query. But I'm just going to do this for fun. So what happens is if I query, I've queried 1 degree of a radius around M45. I'm doing 1 degree because M45 is actually a cluster which is very close to us. It's not very far away. It's the Kritika cluster. I will meanwhile show you the cluster. I hope you can see my Chrome screen and you can see M45. So if I show you M45, this is the cluster. This is the only star cluster which we can see with our naked eyes. Okay. It is called the M45 or the Pleiades or Kritika in India. This is the cluster. This is in Taurus constellation. So many of you all may have seen it. This is the only one which you can see with your naked eye. So you can see that's actually a big cluster because it's very close to us. So its angular diameter is very, very large. Right? Okay. You can also have a look at it on Aladdin. You were introduced to Aladdin by Alessandro, and the easiest way to access Aladdin is you can access the Aladdin Sky Atlas. Click this, and so Aladdin Sky Atlas has two versions. One is the Aladdin desktop, which you can download on your machine, and the other one is Aladdin Lite, which you can run on your browser. In principle, ESA Sky is very similar to Aladdin. So if we get used to using ESA Sky, you will also be able to use Aladdin very easily, right? So now I'm saying I'm querying M45, and you can see that the image will come up over here of M45. So you can actually oh God, this is super zoom, that's why you couldn't see it too well. So here is M45 or Kritika, the same cluster I was talking to you about. So it's exactly like it is with ESA Sky. You can pick up your data sources from wherever you want. This is the DSS image, but you can also, for example, if I want, I can look at it with, if I want to see it with WISE data, this is the all WISE image, this is with WISE. WISE is an infrared detector. So here you can see it in infrared. If I want, I can see it in near infrared using 2MAS. So if I click on this, I can see it in 2MAS. Yeah. So you can see a good number of stars which are there, which will come up in 2MAS. And yeah. So you can see it in various bands using various different data sources. This is similar to what it was in the case of ESA Sky. Yeah, Gaia ESA Sky. And then this one also lets you upload, you can upload all the catalogs and things like that over here using this. So you can actually have overlays. You can have overlay in the sense one layer with infrared, one layer with optical, one layer with X-ray, etc. Put them all over here, stack them all together and actually look at it, right? So this is what the Aladdin thing is. Like I said, it's very similar to Gaia ESA Sky, which you see, but it makes it real fun because you can actually visualize the object you were trying to study. Okay, so let's go back to TopCat. Hopefully TopCat has finished querying, and I think I took too big a size. I'll cancel it, and I'm going to make it much smaller. I'm going to do 30. I think I took too big a size. I was getting a bit too ambitious, because the number of stars you are going to see in Gaia are very, very large, and that is why we have too many things. Yeah, so people are asking what to do next. So if you can open Gaia, if you have downloaded TopCat and managed to open it, then please open TopCat. So I'm like looking at your questions. Kamal is asking any specific reason why it's called a cone. It's obviously a cone search because when I'm looking at this thing, I give a certain angular size, right, of the sky. I'm defining it by a skies in the sky. I'm giving RA deck and giving it a radius. But when I'm looking at from a distance, it actually covers a cone, right? My field of view is now a cone because I have a fixed angular size and I'm looking at it from here. So it's called a cone search. Okay, so it's a circularized, yeah, Alejandro has mentioned circular sky region, and you can visualize it as a cone wherever you look for it, and therefore the same. So what you should do next is open your TopCat and do what I was showing you how to do, which is basically looking for, let's go back to TopCat, sorry, let me go to TopCat, yeah. So we have now got my, yeah. So what I've done is I've downloaded my data. If you remembered, I had pressed VO, I had pressed cone search. I gave my keywords Gaia DR3. Here I gave my object name. I gave the radius size, the size for the cone search I want. And I said, okay. And here you can see here is my data, which is sitting, which is 30 minutes of sky area within the this thing of M45, right? So if you actually see, if I press this button, this one is the stats button. So if I press it, it's actually going to tell me how many objects. You scroll here, you see 6,653 objects, right? Stars I have over there. But if you actually have a look, because of Gaia data, you'll see obviously every source has an ID. So you'll have every source ID and a designation. It has its RA and DEC. That's this thing. But not all stars will have parallaxes because they may not, you'll not be able to measure them. So you can see that the parallaxes is not 6653, it's lesser. Proper motion RA, proper motion DEC also depends upon the brightness of the source and various other factors, the distance of the source. So depending on that, that may not be all the stars, and these other parameters may not be all the stars, right? The Rouvet factor, for example, this is a factor which actually tells you whether it's a single star or it's a binary. So if the Rouvet factor is more than 1.4, then it is it's a double thing. But otherwise, if it is less than that, it is this. But you can see that you have a whole range in that. So that will vary the kind of source that you're having. And by default, TopCat, compared to, if you remember what Alessandro did, when he said select whatever 10, and then he said which exact columns he wanted. If you remember, he wrote RA, DEC, parallax, whatever he wanted, right? TopCat, the problem is it gives you a certain set of columns, and that's the set it gives by default. You cannot change it. At least I don't know how you can change it. So it gives you by default this value of the parameters. So therefore, if I click on this, I can see my table. And you see this table of mine is a huge table. If you actually see when you press this thing, it will tell you how many columns. It's that many columns, right? So many columns are there with so many parameters. It gives you standard deviation, etc. You can actually change these stats to make it display whatever other parameters you want. For example, variance, or you can add in variance, or you can even add, say you want median values, etc. And then you'll have to tell it to recalculate it. So it will recalculate those stats and give you those values for those quantities. Okay, now let us look at the stars of M45. If we plot them here, you press this button. I'm assuming that some of you all who've installed TopCat can actually do this along with me. In case you're having a problem, please write something on the chat window and tell me. Otherwise, I will not know. But otherwise, what I did over here, I'll just repeat it. We go back to this, you click on this window, and here you see it takes the first two columns, which are RA and DEC. So you can see these are all the stars which make up Pleiades cluster, the RA and DEC. But obviously not all these stars are part of the cluster, right? So how can we find out which are the stars of the cluster? The simplest way is, like I told you, these stars all are at the same distance and they are of the same proper motions, right? So the simplest way, which is the easiest one to do, is if you plot proper motion RA versus proper motion DEC. Okay, this is basically telling you the distributions of velocities. Okay, now you can see that there is a bigger concentration of stars which is over here. Okay, and this is centered at, look at the values are shown to you down over here, the position, and you can see this is centered close to 0, 0, right? This is centered close to 0, 0. So actually all these stars are not cluster stars. Okay, because they are centered about 0, 0. So if you had a random set of stars, you will have equal number of stars in the foreground and in the background, due to which their average would be approximately 0. And therefore, all these stars which you see on the upper part are not members of the cluster. They are typically they are foreground or background stars, and therefore they are centered around 0, 0. While this interesting group of stars, which you see down over here, which is centered around something like 20, RA is 20, and PM deck is say minus 46.5. These are the stars which actually are the cluster stars. So I can actually click something called subsets. So Alessandro also explained to you that, which is something which I follow very strongly, that supposing if you have an idea, a research idea, it is the best thing to play around with that idea with Topcat and with Aladdin. And actually you test and see how does your idea work, right? And then based on that idea, what I'm going to show you later today also is a Jupyter notebook which will do exactly what I'm doing now with Topcat. So I'm going to first show you an exercise of finding cluster members, finding distance to a cluster using Topcat, okay? And after that, I'm going to show you how to do that using a Jupyter notebook. Okay, and that's exactly the step which you need to follow if you're doing research. If you're doing research and you have a unique idea, first follow it with Topcat and Aladdin, see how it works, what are the kind of results you get, and then when you want to fine tune your results, you will actually use a Jupyter notebook. So Jeldu Jembola asked me why we write the unit of radius in terms of unit of angle, because we are looking at the sky. We are looking at the sky, and therefore whatever you're looking at the sky, you don't know the distance, you only know the angular size, and hence it is in terms of angle. Okay, Jaltu. The answer is because in the sky we can only see angular distances. We are not seeing real distances. Okay. So now, like I said, these are our interesting stars. So if you see there's a button called subsets, you can click on what is called draw blob subset, click on it, and then if you mark it over here, you will see that this is your drop subset. I can go back to subsets, I can say finish listing, and I can call this club subset C, which is my cluster. Okay, so I will instead call it doesn't like class, so I'll call it class, and I say add subset. So now you see these stars are looking blue, right? So I'm going to repeat what I did just to show it to you. I made a plot. If you see the plot I made was proper motion RA versus proper motion deck. Like I told you, the stars which are centered around 0, 0 are not cluster members. They are foreground, background stars, and hence their average is 0. Our cluster members are these stars over here. So Topcat has a convenient tool to mark subsets of stars. And if you want to mark a subset of stars, what Topcat basically does, yeah, okay, so Argadeep Biswas, after zipping the file, what do we do? No, you don't unzip the file. The Java jar file, you just put this jar file and then you run the command. I will show you Java minus jar. I'll just write the command. I'll get it from that page. I'll write it and show you. Yeah, so.
Open it with Java.
Yeah.
Associated with Java.
Yeah, 1 second.
In
which? Yeah. So, Argadeep, what is your OS? What operating system are you working with? Please write your operating system. Are you
Ma'am,
using?
it's Windows.
It's Windows. Then you should keep the jar file and associate it with Java. Okay? Associate. So when you say open with the, say with Java.
You have to install Java.
I hope you have Java on your system. You may and should have Java, right? Okay, so we'll go back to our plot and this and this. Okay, so you see that these are my stars which I had marked. How did I mark it? I press on subsets. I say draw blub subset. I mark these stars, right? I say I finish drawing blub subset and I save it, okay, with some name. So I save those files as class and therefore you can see these blue stars. So now what I'm basically saying is that these stars, if we go back to our earlier plot, these stars, I said, if you look at the RA deck plot, I'll plot it again. You can click on subsets. I can say all and I can say class. So according to me, only these ones are that. So all stars, I'll make them a little lighter so that they don't look too dark. And the cluster stars are the blue ones, easier to find. Okay. Now what happens is I know all these stars should be at the same distance also. So what am I going to do? I am going to make a histogram. I place one histogram of the parallax. Okay. So I'll make a histogram of parallax, but distance is 1 upon that. But now again you're seeing I have two bumps. I have one bump coming over here and I have one bump coming over here. And exactly in the same way like we did in the previous case, the bump closer to 0 is obviously these stars. Okay. So if I here click on subsets and I click class, you'll see most of the cluster stars are this bump, not this bump. Okay. There are some stars sitting over here, but essentially these are the stars which are the cluster stars which are at this value. So if you see, this position is giving me something like 7.5. Okay, I'll show you how to fit that to a Gaussian, but before that let us see. So you see these are the stars and these are the stars, and therefore I decide my cluster stars are not obviously these ones which are centered around 0 parallax, they are these stars. And therefore in TopCat you can do it again by marking it, or you can even just zoom this out, and if you just do it, you can even do in TopCat something which is called subset from visible. So I can just choose these visible stars to be my subset. So if I take this one, right, I can say this one is my subset from visible. And now I can call this, say, class 2. Okay. So the first set of stars were the stars which moved with the same velocity. The second set are the set of stars which are at the same distance. So this gives me my class 2. And if I want to know the actual distance to my cluster, it's obviously 1 upon parallax. But you see, this is the distribution of parallax. And therefore, I can fit this to a Gaussian, right? I'll show you how I fit this to a Gaussian. There's something called form. So click on form and I do forms and I say add Gaussian. So I have an Gaussian which is added onto this, right? And let me just put it for class 2. So you can see that there were Gaussians for each of the distributions. I'm just going to put the one which is for my class 2, not for all, but for class 2. This is the Gaussian. And if you actually click on form, you can see the value of the Gaussian. It tells you that it's 7.36, okay, with a standard deviation of 0.16. Now, just to let you know, Gaia data is in the units of milli-arc seconds, okay? A milli-arc second is 10 power minus 3. And therefore, when we are doing 1 upon parallax, your milli-arc second becomes 1,000 divided by that. So now if my parallax is 7.36, my, my distance therefore becomes, 1,000 divided by 7.36, right? And that value you can see is 135.86, okay? So that means the Pleiades cluster is at a distance of 135.86, okay, parsecs. This answer will be only in parsecs because our parallax is in arc seconds, right, milli-arc seconds. So when you convert parallax from arc seconds, it is in parsecs. So it's approximately 136 parsecs is the distance to Pleiades. And the final step which you'll need to do is for these. So if you want to see these stars, I can show it to you. These guys, I'll close this one. But if you look at these stars, I can actually show you their motions, okay? By basically saying form. Again, I click on form. And the form, I call it a XY vector. Okay, I call it an XY vector. And if you can see that my XY vector is basically made up of vectors which are proper motion RA and proper motion dec, right? So dec, and you can see it. So I'm not going to keep both the subsets, I'll only put this. Let me make it a little nice and dark so that you can see it better. So here, you can see these are the members of the cluster. If I were to plot all these stars, right? If I were to plot all these stars, you actually can't even see it properly because all the velocities are in all directions, right? I can just show it to you. But if I were to plot all the stars, I'm scaling it, but you can see all the stars obviously have velocities in all directions. And therefore, these stars are not stars which are connected, right? They don't belong to the same star cluster. They are moving in all different directions. But we identified our members of the clusters as stars number 1, which have the same velocity, and number 2, which are at the same distance. And therefore, if you actually see in the plot, you can see that we have these. But obviously here, for some strange reason, I seem to have these outliers. You can see I have these outliers which have this thing. Maybe the reason being that I was a little careless in taking outer stars. Maybe I should have just taken inner ones. Let me just redo it once again. So I'm going to define my clusters subset. Let me define it once again. I'm going to be very careful, and let me say I'm going to take only very inner stars, very much inner stars, because some of these maybe are not good. So I'm taking a much smaller group. I'm saying I've burned it. Now let me call this class 3. Okay. And now when I plot these guys, let me do them here. And I'll put them in a lighter color. And here are my class 3 stars. But now my class 3 stars, I didn't correct them for parallax. But let's see, because I've taken them so in such a strict manner, maybe I would not even require parallax correction. But let me take my xy vector and let me do this. So I'm taking this. Yeah, here is my thing. Yeah, so now here you can see. I'll try to make these stars, the class 3 ones. Okay, they are quite dark actually. So not a problem. I think I don't need to darken them further. But if you can see, here are my stars and they are beautifully moving all together, right? Because I've been a little bit more careful, and you can see all of them are moving in the same direction. So you can very well differentiate the cluster stars from the non-members. And then the final step in a star cluster is the plotting of the HR diagram, right? So Gaia data gives us photometry. So Alessandro already mentioned it. The color is the BP minus RP factor, which is over here. And the brightness, you can take any magnitude you like. Let's take the G-band magnitude. Here's the G-band magnitude. I'm going to rotate the y-axis because astronomers, we like it the other way. And now here you can see how very beautifully when I plot my cluster members, wow, you can just see that. You can see here all the stars are sitting in this, these pink guys, which are all over here, but the cluster members are these. All these other stars are not cluster members. So the clean HR diagram which you have for M45 is this. You can see obviously there are many over here, and basically these are fainter stars, and these fainter stars, in their case, there are much larger errors in these things. Similarly, even these stars, they could be outliers. One needs to check them. If you see very beautifully in TopCat, if I mark a star in one plot, it comes up in the other plot. So I can actually check it out as to where is it in my proper motion plot, where is this star, where is it sitting, why does it seem to be behaving the way it is, right? So these stars, you can see, these are all basically fainter stars. You see their magnitude. These guys, this one is, for example, magnitude 20th magnitude. This one is 18.4. So these ones are fainter ones, hence the errors are larger and they've been wrongly identified. So these ones are for sure the members of the cluster, and this is what we call a clean HR diagram. That means a set of stars for the star clusters. So this is a very simple exercise which very often we even teach it to high school students, because this kind of an exercise does not require coding skills, but it at least requires an important understanding of what is a star cluster, and that star cluster stars have the same velocities the same distance, etc. So using those two basic pieces of information, we can place them like this, and in that way you can this thing. A final step would be where you actually plot this thing as cluster 3, and I can save this as a certain file. I can save this table and I can call it my, I can say my M45 members, right? And I can save it best as in VO table format, right? And I can go back to my plot which I had of Aladdin. And in my Aladdin plot, actually I've never used this Aladdin light. So when I do Aladdin light, openly the overlays menu. Okay, so I'll say overlay, catalog from a VO table file. Okay. And let me write M45. What did I call it now? M45 mem, no? Or did I call it with capital M? M45. It's going to Mac. One minute, I'll just verify what did I name this file as? Class 3, and I said save as view table format. Acha, M45, acha, bam dot this thing. Okay, so I'll do that and I'll say okay. I'm sorry, I was looking for the wrong name. Come on, where is it? Why can't it find it? Why is this doing this? Why is it going into this place? I'm sorry, 1 second. Let me just redo it. I don't know why is it creating a problem like this. Did I do it or no? Yeah, override, it's already there. M45 mem, yeah. So why does it have a problem? M45 mem dot VOT. Why is it searching in this map? Huh?
Close the top and see.
Actually, I never use this, I never use the light.
Shut down your Tomcat.
No, but I'm using Tomcat. How can I shut it down?
Then maybe write it at that.
Okay. I'm not too sure why is this not happening, but it will happen. I'll do it with the standalone Aladdin. Just a minute, just a minute. I will stop share and I will start my standalone Aladdin. I can't close it, Najam. Okay, so what I was just trying to do is I want to overlay on that file and show you the position of my members, right? Only like I said, I generally use this is the Aladdin which I'm using, which is sitting on my system, right? This is not the Aladdin light from the browser. I generally use this one, and hence I will prefer to use this. 1 second, just let it load. I'm sorry. Right, so in this exercise, basically, have we identified, how could we identify the members of a star cluster? Like I said, using the basic logic that cluster members are the same distance and they have the same velocities, right? So what I'm going to now doing is that the members that we have actually find, I'm going to overlay that onto the image which we have of M45 so that you can see which of these stars are actually members of M45, okay? which we did as per analysis. Now, this analysis is a very rough analysis. If you saw the way I marked members, I just, I didn't check their values, I didn't check the standard deviations, etc. But if you do it in a Jupyter notebook, then you can do it in a way in which you may more carefully check values, right? So this is the same Pleiades cluster, which I've plotted using the under Aladdin. This is the standalone tool, okay? That means the one which you can download onto your system, okay? Now over here, I can overlay my catalog. Let it get activated. I'm going to put load my local file. Now it's going to 45. Oh God, it's again going to torture me. I'm sorry. M45. Did you find M45? Here, that's our file. That's the one we want. And it has to be in the VO table format. Where's VO table format? It says it's a FITS format. Okay, so now you can see over here, let me change this color. Maybe red is not so obvious in your screens. I'll make it green, or should I make it yellow? Is yellow a little bit more observable? I can also try to make it a little bigger. Right, I can, whatever this. I hope you can see it on your screens. Can you all see it on your screens? So in short, you can see that these guys, these bright stars, they're actually not coming out as members, but you can see these fainter stars coming out as members, right? Now, this is another caveat in Gaia data, that very bright stars, they saturate up the CCD. And therefore, this doesn't mean, I will not comment on it just now, I will leave that as an exercise for you to check out whether these stars are members or no. So problem is in Gaia data, their brightness is too bright, so they will saturate all the pixels of Gaia. And hence these guys you see over here are not getting marked as members, right? These brighter stars, but the fainter ones are, there are a good chunk of them which are getting identified as members, and these are the members. The problem with the brighter ones is because they are bright, they are getting saturated, right? So I'll end with this thing, which is this basic exercise of how finding out the members of Pleiades using TopCat and then plotting them on Aladdin, right? We'll now take a break from this and we'll get on to a Python exercise, after which I will do another exercise where we'll repeat the same thing using a Jupyter notebook, right? But now I'll hand it over to Najam and he'll talk to you about basically use of Python and AstroPy. So I'll stop with this and I'll take immediate questions if they are very urgent. I'm sorry I couldn't wait for all of you all to do everything, but otherwise we have a very tight schedule and we won't be able to finish. So you can then see the recordings later on and hopefully, cover it up, right? So Najam sir will continue now with Python. So I want the YouTube.
Yeah, so hello. I will start with Python. And those who are familiar with Python, just be a bit patient because there are some who, half the number of people say they are novices at it, and half of the ones go to the intermediate state. So I'll start off with Python in a very basic way. But very soon we'll get down to AstroPy so that we can start working with astronomical data and catalogs. Okay, so I will be using Jupyter Notebook. Jupyter Notebook is something which we really like to use. It's up to you. You can use Spider, you can use PyCharm, whatever. But Jupyter Notebook somehow is good enough. And I'll be starting with Jupyter Notebook. I hope some of you are familiar with it. So I'll start it again. So those who are in Windows, you click this Windows button and type Jupyter Notebook. Anaconda is a good way of installing Python and most of the essential packages with it. And if somebody needs help in that installation, you can write in the chat box. Anaconda is a good way of downloading it. And yeah, so I'll start off with, say, a new notebook and get down to some very basic things of Python. This is for those who know nothing about Python. So Jupyter Notebook has this kind of an interface where you can change a cell from code to a markdown one and vice versa. Okay, so if in this window, if I, at the simplest level, Python Notebook works
Sorry,
like
we
a
cannot see
calculator.
the screen.
Okay, you can't see the screen.
Entire screen currently.
Yeah, can you see now?
Yes.
Yeah.
Yeah, but
yeah.
zoom in.
So, thanks for telling me. Yeah. So at the simplest level, Python Notebook, Jupyter Notebook, it works like a calculator where I can say add two numbers, multiply two numbers, or I can find uh, exponent of two numbers, 4 to the power of 6, and so on and so forth, where you can do division, division and multiplication and so on. And you have modular division, you have, if I use percentage, then I get the modular division, that is, it gives you a remainder, and so on and so forth. Uh, so this is something very basic. A small nuance of, yeah. Another thing is you can define variables. Say A is 7, B is 9, and you can say what is A plus B, and it gives you the value, right? So you can define variables. The variables can be integers, they can be real numbers, they can be complex numbers, they can be lists, or so on. For example, I can even have a list, say, of 1, 2, 3, 4, and whatever, and I can define a list and so on. Okay. Now, since I said it can work as a calculator, if you try something, you would expect it can do a lot of mathematics, which is true. But suppose I want to do sine of 32, and you will see that you will get an error. It doesn't know what sine is. Okay. So there is a package called maths package in it. There are many such ones. And if I say uh, import math as m, yeah, this is the way we generally do it. And if I say m dot sine of whatever, I'll get it. So yeah, so by importing the math package, and I'm giving an alias called m, and I, instead of writing math all the time, I say m dot sine and so on. Similarly, now once you have done that, you can say that m dot cos of 78. And so these are in radians. If you want to have it in degrees, then you have to convert it. And this is the cosine of that and so on. So if you say put m dot and press a tab, you will get all the functions which are defined in the package, right? So there are many pi. For example, I have m dot pi is your pi value, right? So the constants are defined. And m dot tab will give you all the possible functions which are there. Okay. So you need to know them all, but as you are using them, you can get to see what are there and what GCD, log 10, and nan, pi, power, pod, radians, sine, tau, and so on. So there are many such things which has to be done. Okay. Another thing which we probably would want to do is to plot functions. Okay. So suppose I want to plot a, I want to plot a line. Okay. So we are looking for plotting a straight line y equal to 2x plus suppose 8. Okay. So yeah, so I'm going to plot this line. And for this, I would want to give x ranging from 0 to 10 or 0 to 50, whatever, and calculate y's for that and then plot it. So we require something called NumPy. It's NumPy and Pandas. They are two modules which I will introduce very briefly, which we will be using as we do other things. So import NumPy as NP. Yeah, this is a standard way how you do it. And I'll be doing for plotting, so I'll import mat matplotlib dot pyplot as PLT. Okay, so matplotlib dot pyplot as PLT. So for those which it sounds cryptic to you now, don't worry, you'll get used to it. This is how you import different packages. So when we are saying import numpy as NP, it's something similar to what we had done earlier, import mat as M. And matplotlib, instead of writing matplotlib dot pyplot dot something, I'm calling the whole thing by an alias called PLT. Okay. So now numpy has a function called linspace. So I say x equal to np dot linspace, and suppose I want to go from -10 to 10, and I want to have 100 divisions of that. Okay. And remember, you have to either press this button or say run the cell, or you have to, whenever you want to execute a cell, you have to press shift and enter. Okay, and if I write X and I press shift and enter, you'll see that it has started with -10, minus 9.779, 9.95, all the way up to 10. Okay. Suppose I had said from X is from 0 to 10, and I just take say 5 steps of that. And you see, you just get 0 to 10 with 0, 2.55, 7.5, 10, and so on. Okay. So, and now I feed in the equation y equal to 2 into x plus 8. This is what we wanted to plot. So I've now defined what y is. And if I look at the values of y, I'm getting 8, 13, Yeah, so it's 2x plus 8. So 2 into 0 plus 8 is 8. Then 2 into 2.5 plus 8 is 13, and so on. And these are the things. Okay. And now I use the matplotlib to plot it. So I say I have plt dot plot x comma y, and you see this is the line, right? So NumPy is pretty useful, and this linspace is something which we are going to be using pretty often. Okay. And this NumPy has even things like np.pi will give you the value of pi, and various constants are defined. Similarly, np.sign, you don't have to invoke the math package. You can use np.sign. So NumPy has a lot of mathematical functions and things in it. So for numerical work, NumPy is of much use. Okay. So this is for NumPy. Those who are familiar with Python, I'm sure they would have known what, they know it very well what these things are. And now I will go into, uh, uh, I'll do a little bit of pandas. Okay, so similarly as we have NumPy, we have pandas, and we'll do a little bit of data wrangling with pandas. So my idea is to show you how Python works, do very little of NumPy, what we have done, very little of pandas, and then we'll get into AstroPy. AstroPy is the one which will be very helpful for astronomical work and so on. Okay, so what is data wrangling? It is if you have data, if you want to sort the data, you have to filter it under a criteria. You want to reduce um, unwanted values, right? There are outliers in it and you want to get rid of them. You want to read and write them from a file or write it into a file. And then if you want to do some statistical work with it, finding mean, median, mode, and other things. So this is what is uh, data wrangling in pandas. And here again, we start off by importing pandas as PD, and there is a function called data frame. I hope you can see it. And I say PD, since I've called pandas as PD, now I will have PD dot whatever function. So PD dot data frame. Here, data is capital D and F is capital F. And I'm storing, it's a blank, it's an empty data frame. And I'm uh, putting it into a variable called df, right? You can put any name you like here, but I'm calling that variable, say df, and I'll print this data frame. And when you print it, you see it is empty data frame. There's nothing in it. It has 0 column, 0 index. Now I'll create a simple data frame which say a list with these 3 elements. Right? So ls is 67, 8, and 9. And if I say pd.dataframe ls and store it in df1, it will, I'm creating another data frame. Yeah, I'm just creating another block here. Yeah. And now when I print df1, you see I have created this data frame, right? It has one column with 67, 8, 9. Okay. So first I showed you how we create an empty data frame. Then I showed you how we can pass uh, a list into it and convert it to a pandas data frame. Now I'll get a little more uh, and create a table, a data frame with some data in it. So I'm creating a dictionary of data where the first column name is ID, and these are the ID numbers. Then the second column name is name, where I'm giving names of people. I found some names in our chat box: Olga, Natasha, Prachi, Rajan, Newton, Aditya. I just picked up some, Nancy, Ayush. And I'm giving them, attributing some randomly. I've given marks. Don't get bothered whether I've given high marks to someone and less to another. And I've given these marks 89, 97, 3, 4, so on. And then I'm attributing some grades to it. And this dictionary which I have of data which I have created, I can again use this PD data frame to create create this data frame called data. Yeah, I'm calling it data this time. And when I print this data, I'm seeing you can see that this is the table which I have formed. Yeah, so data frames basically are uh, um, they are tables in which it can have multiple columns and multiple rows, and the columns can be of different types. It can be an integer, the other column can be a string, the next column can be uh, marks or floating point numbers, the third can be some uh, strings again, and so on. So these data frames are made up of, these are essentially tables like we would have in astronomy tables that VO, Priya ma'am just showed you how to save the cluster members in a VO tables format through TopCat. So similarly, you have tables available on the net in the astronomical archives, and we can convert them into data frames. And the beauty of, once you've converted these tables into data frames, there's a lot of work can be done very easily. For example, now when I have this frame called data, if I just run the command data.describe, you'll see that it gives you some basic statistics of the whole thing. It's the first one says there are 9 entries in it, right? So from 0, Olga, Natasha, Prachi, Rajan, Aditya, Nancy, there are 9 of them. And the marks are also 9, and everything is a 9. Okay. Then wherever possible, it is doing statistics. It couldn't do statistics with ABCD, but wherever it had marks and all, it has done it. And it shows that, uh, yeah, ID number also is calculated the mean, median, mode, which doesn't make sense. But anyway, it saw numbers and it could do statistics, so it did it. So what we have now here, in one go, data.describe, we are getting to see that the mean of marks is 78.77. The standard deviation is 18.123. The minimum is 45 and maximum is 100. The first quartile is 76. The second quartile, which is also median, is 81. And the third quartile, which is 89. And yeah, so these quartiles are important. This median is the middlemost value. It shows how the data is, where is it distributed. Around 81, half of the data is lying on its left and half is on the right side. While this 25 quartile gives 25% on its left and 75% of data is on the right, and so on and so forth. So by looking at mean and the standard deviation, the variance, we can find out a lot about the data. Okay. Another very interesting and important thing is why data profiling in pandas. So if you import why data profiling as PP, I'm giving some name. Okay, and then I run this command. Then I run this command pp.profile report. In why data profiling, there is a function called profile report. Notice that P is with capital and R is capital again. All others are small. So I do pp.profile report of data, and it is to get executed. Yeah, it got run. And now when I want to see this profile, you just a minute and it will load, and you will notice that it does the whole, it creates a whole report of your data. So see, there are different tabs here: overview, alerts, reproduction, variable types, and all that. So the first tab shows that the number of variables are 4, number of observations are 9, missing cells are 0, missing cell percentage is 0 again, duplicate rows are none, and so on. So in case in a table there are duplicate rows or so, it will show up. The missing values will show up. The average records are there. Okay. And if you look at the variables, you will see that uh, for ID, yeah, we are not interested in ID, but ID, there are 9 of them, and the mean is this, and so on and so forth. Then for marks, it gives you the whole statistics which we got from describe as well. But further, if you see, it shows you relationships. It plots ID versus marks, and you can choose what all you want to um, plot what against what. It gives you correlations, it gives you missing values, it gives you samples, and so on and so forth. Okay, so a simple command like data.describe will give you the all this basic statistics of the data frame called data, and pp.profile reports creates the report in all these things. These profile reports can also be saved as HTML files, right? So I've commented this, and if I have not done that, then once it runs, it will create an output HTML file, and it will sit in my home directory, and you can use that anytime you wish. Okay. So this is okay. Now coming to uh, closer to what astronomy this workshop is going to let you handle. I have a, uh, a file of M3, Messier 3 object in comma separated variable format. Okay. Yeah. So uh, uh, okay. So this file, I want to read it into this in Python, and then I would like to do various analysis of that. Right. So when you download your uh, tables or catalogs and so on from archival sites, you'll you can save them as comma separated variables, tab separated variables, or whatever. And the pandas allows you to read these comma separated variables or Excel files and so on. And the command for that is pd.read underscore CSV, comma separated variable. If it was in Excel format, we would say pd.read underscore Excel, so on. Okay. So I have this m3.csv running in my home directory, and I'm using this pandas read underscore CSV function to read this file. So I run it, and when I want to see the data frame, I see this is what it is. So you'll see it as 36,424 rows. It has not printed all of them here. It has shown the first 5 and the last 5 rows. Okay. But you will see that it has 36,424 rows and 6 columns. One is RA, second is declination, parallax, proper motion RA, proper motion dec, and kilometers per second. Okay. The radial velocity there. And now I want to convert this into a data frame. Yeah. So I'm converting this data into a data frame by using pd.data frame into df. And then with df, I can, if I say df dot header, I if I put 2 here, I will see the first 2 uh, uh, rows of it. If I write 5, it will give me the first 5 rows. And similarly, there is a tail command. There is a tail command with which we can see the lower end of the thing. Yeah, tail, and I say 7. It will give me last 7 rows. If you don't put anything in head or tail, it will give you the default 5 ones. Yeah, if I don't specify a number here, I'll get first 5 rows or last 5 rows. So with this, we can inspect the table. And yeah. Now, using the same describe command which we had used for the table we had created with marks, I run this command df.describe, and it shows me that there are 36,424 RA entries, same number of deck entries, but parallax I just have 25,942. Yeah. And PMRA is also the same amount. PMRA, PM deck are same. Parallax is also same. But for the last column, radial velocity, we have only 50 entries. We don't have many of their blank columns there. Yeah, so there are many missing values in PMRA, PM deck. And then it is giving a table with mean, standard deviation, minimum value, maximum value, first quartile, second quartile, which is median, and third quartile, right? Everything for each one. Right ascension, the mean is 205.54, standard deviation is so much, and so on. Similarly, you can find out parallax by just looking at the table. You'll find out from minus 27.6 to it's giving 39 parallax, right? So obviously this minus 27 parallax doesn't mean anything, but it is showing you how they are being arranged, and it is giving you the whole statistics of the whole thing. Right. Now if I do the profiling with this, I say profile equal to PD dot y data, no, profile report, PD profile report yeah, PD profile report of what was it called, DF, of DF. Yeah. What is the DF tail DF? Yeah, profile report of data.profile. Yeah, just a minute. Where did I go? Yeah. Yeah. So sorry, I should be writing here. DF dot profile report. PP profile of data. Yeah. So I do PP profile reports of DF. And I take profile report of DF. And then I do the print the profile. It will create the profile report. Yeah, so for the whole database. Okay. So here you will see this makes more sense than what it was done previously, because there was only one set of marks. If we had marks in 2 or 3 subjects, we could have done. So it gives you the whole statistics of the whole thing, and you can see you can have histograms for how RAs are distributed, how declinations are distributed, how parallax is there. All right, then we can find the relationship interactions between them. We can have RA versus declination. Yeah, RA against dec. Yeah, you can plot parallax PMRA versus, right? So you can find the relation between any two of these. You can find the correlations which are given here. It gives you the missing values, and the whole report is given in just a click of a button. And the same way, you can save it into a file if required. Okay, so you can save it into an HTML file. I'll share this uh, notebook with you all so that you can run it, and you can download different data sets and run this and save. So the advantage of using Jupyter Notebook is once your code is done, once your notebook is running fine, you just need to uh, you can run it on multiple uh, files at the same time. You can have one template, and you can, when you're analyzing 3, 4, or 100 clusters, you can automate the whole thing, and it does one by one the whole thing. Okay, so if there are any questions, we can stop here. Otherwise, I can proceed to AstroPire.
You want me to take over? But you're doing fine, that's all. You want to do it?
Just see any questions. Yeah, so if I hope everybody is following, and so with these very fun basics of pandas, data frame, NumPy, and Python, we'll now get into AstroPy. which will be of much use when you are doing work with your astronomical data sets. So here's something on AstroPy. So what is AstroPy? It's a single core package for astronomy in Python. AstroPy package is structured into several submodules, and we'll cover a few of those. One is the units, one is the coordinates, then how to handle astronomical data as in table format, and the FITS files. How do you read FITS file, and how do you write a big FITS file, right? I've also given you a set of resources. The best thing with all these is VO and Python. You have a lot of community support on the net, and there are a lot of tutorials and documents which help you learn it and use it your way, right? So here I learn AstroPy, AstroPy documentation, AstroPy tutorials. So that these are hyperlinked. So if you just click it, you'll go to these repositories and you can learn AstroPy on your own. Okay, so here are some commands which are familiar to us. Import matplotlib.pyplot splt, which I have done it while trying to plot that straight line, and import numpy as np, and import astropy. Yeah, we are importing astropy. These two commands are not very important, but suppose, yeah, so I'll run them, and the other two commands will give you the numpy version, and the numpy running here is 1.26.2, and the astropy version is 6.010, right? So these are just for you if you want to find out version, which version are you running. You can use this for others, so pandas and so on. So as of now, what has been important till this stages, we are importing matplotlib pyplot as plt, and numpy as np, and astropy. Okay. Okay. So now in astropy, so exactly like we had done import uh, sine and cos from math package, I'm from astropy import units as u, right? So I've imported astropy, and now from astropy, I'm importing units. So it has a sub package called units, and this units is used to convert light years into parsecs, parsecs into light years, into kilometers, into miles, into kilometers. You can, all the units which are used, astronomical unit or you know, uh, light years or parsecs, when you want to convert from one unit to another, then this comes very handy. Okay, so from AstroPy, import units as U, and now I'm defining a variable called distance1 as 1 dot into units AU. Okay, so this distance1 is 1 AU. I'm calling distance1 as 1 AU. Okay, and distance2 I'm defining it as U dot light year. Okay, so it is in terms of light years. So now when I want to convert light years to meters, I say distance2 is, we have defined it as 1 light year, right? So when I say distance2 dot 2 meters, it will give me how many meters is 1 light year. Similarly, if I've written centimeters here, convert distance to centimeters, yes. So it will convert it into centimeters, as simple as that. 9.46 into 10 to the power of 17 centimeters. Okay, so now I will define u dot parsecs. These are for parsecs. Like you all know, 1 parsec is 3.26 light years. And now I'm defining the distance as 1 parsec. And converting 1 parsec to meters is as simple as using this distance 2.2 to meters, and it will convert it to meters. Okay. And right, so similarly you can convert it to light years. So I'm converting it to u dot light years, and it converts distance to light years, 3.2615, right? So because distance was parsec, okay. So this units makes it very convenient to go from one to another and so on and so forth. Okay. So similarly, you can have speed of light as distance by u year in 1 year, and you can say print the speed of light. Similarly, you can convert it to angstroms per day, and there it is. Okay. So not just that, but suppose you have a list of distances 1, 6, 10, right? You have many such. I can define this list distances and multiplying it with the unit of light years. So all these will be 1 light year, 6 light year, 10 light years. So now when I use this distances, this is 1, 6, and 10 light years in it. Okay. So similarly, we can do these. Okay, distance light years to unit and okay. So I will share this with you, and this command type function tells you what type of variable it is. What is the data type? So when you are running this, it shows it's a NumPy array or whether it's a pandas data frame or what it is. Okay, so type is an astropy. Why when I say distance dot units, it's an astropy unit score in units. Okay, so these are the things, and you can uh, do all kinds of calculations and so on. Now coming to constants, there are certain constants which are stored in astropy, and so from astropy import constants as constant and print constant c to kilometers per second. So if what I'm doing is the speed of light I'm converting to kilometers per second. So it is 299,792 .458 kilometers per second. The constant c, if you press, then you have 2.99 this 10 to the power of 8 meters per second. Similarly, there are these, so we are importing constants and constant. So constant dot c, constant dot sun, like r underscore sun. This is a constant which is defined, and it will give you the radius of the sun. So you say constant dot r sun, and it gives you 6.9. Okay. Similarly, mass of earth, mass of sun, you have it. So a constant m underscore earth. Similarly, there would be m underscore sun. So suppose I create one more here. So I suppose I have write constant dot m underscore earth. M earth we have sun, mass of the sun. Oh, S is missing here. Constant m sun, and we get 1.98 10 to the power. Yeah, 1.98 here, 1.99 almost 10 to the power of 30 kgs. So similarly, you have if you look at this, you have a list of constants which is there. You have capital G the gravitational constant, n underscore a is Avogadro's number, r is gas constant, and so on. So all these constants, electron charge E, H, there's a GM Earth, yeah, nominal Earth mass parameters, for Jupiter, mass of Earth, mass of Jupiter, mass of Sun. So there are many such constants which are already stored that which you can use it very conveniently. Okay, so yeah, sorry, yeah. So here we were. So if you just click this list of constants or Google search for list of constants in AstroPy, it will give you all the constants which are defined, which you needn't um, check and do. Okay. Now another important thing which we are required to do, we stop for a minute.
Forget it.
Yeah. So we'll come back to these coordinates after a short break. I think it's tea break for you. So we will stop here and come back after half an hour. Then we'll do coordinates and how to handle FITS files. And then we will do some hands-on sessions with through Jupyter Notebook.
On the chat only, actually, you can attach and share the notebooks with them.
Yeah, and I will share this notebook now. So during your break, you can run these things and check it out. And those who require help in installing Python, you just let us know, and during the tea break, we can do it. Any questions? Are you following or are you having problems? Are you all back? Shall we start? मेरी आवाज आ रही है? Can you hear me?
Yeah, yes.
Yeah. Okay, so there are a few people who are saying yes, that we'll start. And have you been following what's happened, or because in this online sessions we just don't get an idea as to what's happening, whether you all know all this and we needn't do, or we are going too fast or too slow. So some kind of a feedback would be good. Are you getting the general idea of what's happening? Should I continue in the same pace? Okay. Yeah, okay. So I've shared the Python notebooks in the chat box, and I've also shared one FITS file and one data file, m3.csv, comma separated variable file, which is for the M3 Messier object 3, which has 6 columns and 36,000 rows, which you can just play around and check. And also the FITS file, which we should be using now when we handle FITS. Okay, so yeah, so now let's continue. Yeah, okay, so let's have a little bit of recap. What we did was import AstroPy, and from AstroPy import units as U. Yeah, we are importing units and we are importing constants. So import AstroPy from AstroPy units as U, so that we don't have to write units. Otherwise, here we would have had to write units dot parsec, units dot something, right? Exactly like if I say import math, then if I want to get sine, I have to write math dot sine dot 78. Okay, only then it will run. But what we do is import math as M. It is basically to reduce our work of not writing math all the time. Only M dot this would work, right? So yeah. So in this case, AstroPy units, AstroPy dot units dot whatever instead of writing, we just write it as U. So now if I say X is 1 into U parsecs, U dot parsecs are units parsecs. So when I see what X is 1 parsec. And then we have seen how to convert parts, to other things. So the method is dot to, and whatever you want to convert it, you write it. To meters. Meter, see, it is in inverted commas. Okay, to meters. Similarly, I could convert it to kilometers. So 1 parsec in kilometers is 3.0856 into 10 to the power of 13. Okay. But remember that if I want to convert, I'll just create one more block here, a few here. If I want to convert, say to, yeah, to just try if I say x dot 2 and I just write meter instead of putting it into inverted commas, you'll get an error. Okay. So it's necessary that you put it in inverted, yes, and then it is fine. Similarly for kilometers. But if you are converting it into parsec, say I have all the right to convert this parsec into light years. So suppose I want to convert this x to light years. So here I say u dot light year. So it is, yeah, so x was 1 parsec and it is converted to light year. Notice that I am not putting inverted commas here. If I put this here, I'll get an error. Okay. So when it is these units which you are using from units, then you don't put um, the inverted commas, but otherwise you would. For meters, kilometers, you would do it. So similarly, I can define y as light years. One is 1 light year, and y2 meters is this, and to parsec which is this. Okay. So this is what we had seen and all other conversions. Another thing which we saw is there are many constants which are stored, saved in this astropile. So you needn't look up or remember them, like gravitation constant G, like Planck's constant, and mass of Sun, mass of Earth, mass of Jupiter, radius. So there are these, and so from astropy import constants as constant. Okay, I'm say I'm importing constants at Don't say import constants as C, because C itself it is u dot c is speed of light. So constant dot c is speed of light, constant m is mass of sun, and constant c to kilometers per second. You use the same constant dot c 2 kilometers per second, and it does that. Okay, so continuing with that, so this is what we did before the break. Now we'll come to another important thing of handling sky coordinates. So as you know, location of astronomical objects, we have different coordinate systems which we describe where an object is. One is alt-azimuth system. What is the altitude and what is the azimuth? But the alt-azimuth system is fine when it is used locally. But if you move from one location on Earth to another, say from India to Japan or to Brazil or to Germany, the altitude at which you will see an object and as would be different for different locations. So that's why astronomers use right ascension and declination. Okay. So right ascension and declination, they are the same coordinates for all observers on Earth. And what are they? You take the axis of rotation as your reference line. Yeah, you have the celestial sphere, and you have the axis of rotation extends to the pole star. You take a plane perpendicular to this, which forms the equatorial plane. So even the same as Earth's equator, if you extend it to meet the celestial sphere, that will be the same one. And you measure along the great circles what is the angle from the equatorial plane to that point, which will give you the declination. And RA is you project it on the celestial equator and you measure the angle from the first point of Aries down to this, which gives you the right ascension. So right ascension and declination are the other coordinates, and these are universal ones. They change over a period of time only due to the precession of Earth and with small changes in the motion of objects. So every 50 years they release new sets of coordinates, and they change by a very small amount. Other than that, we have galactic longitude, latitude, where from sun to the galactic center is taken as 0 longitude, and all around as you go anti-clockwise you have 90 degrees, 180 degrees, which is anti-center, 270, 360. And then above the galactic plane you have the number of degrees. You have galactic latitudes, 10 degrees, 25 degrees, 90 degrees is straight on top, and similarly galactic latitudes which go down, right? So you have galactic longitude, latitudes, and so on. So there are different coordinate systems which are used, and here we will see how to convert one from another, or even find objects through our Jupyter notebook, locate objects and download data using these. So from astropy.coordinates import sky coordinates. Notice that it is capital S and capital C. All others are small. And then I know that you can Google search for Crab Nebula. Here, let me search for Crab Nebula sky coordinates. And here we have, yeah, 5 hours, 34 minutes, 23 seconds, right? These are but in degrees, if you want it in degrees, that is you will see it is, yeah, 83, 83.633 degrees and 20 degrees declination. Okay. So that's what we are doing, 83.63 into degrees, unit of degrees, and 22 unit degrees. And the frame we are using is ICRS, International Celestial Reference System. Yeah, that is the frame of reference. And we are taking the sky coordinate so many degrees and so many degrees, longitude, latitude, in this RA and declination. And we are defining as the position underscore crab. Okay. And when we print it, we are seeing the RA and declination as this, as we have given it. Okay. So we can convert this to sky coordinates into, suppose we have sky coordinates 345 to 3 point this degrees, and the other ones in degrees, and we want to convert this to galactic frame. We are getting, yeah, in the sky coordinates, galactic longitude, latitude. We have converted these two into these, right? So it's as simple as that. So once you have this RA and DEC, I can put those values here, and I can convert them from degrees to galactic frame and so on and so forth. Yes, similarly, you can get the position of crab in terms of our 5 hours, 34 minutes, 31 seconds, and right. So this will also do. So when we had searched it, we had got these values, 5 hours, not in degrees, but in this hour angles. Okay. So Sky coordinates will allow you to pick up in shells. So only when you are using it in degrees, you specify in degrees. Otherwise, you give it in terms of hours, minutes, and seconds. Okay. So these are the same thing, and we are getting the same value. Okay. You can also get the position of an object from their name. Yeah. For example, I want to find out what is the Messier 13's position. So I'm defining a variable called pos M13, and I'm using the sky coordinate and dot from underscore name, and now when I print those ones, I am getting the array and declination of this object. So you can Google search and check. You can check that these will be the coordinates for M13. Yeah, so similarly, if you want to find out for M3 or yeah, and I'm printing for M3 now, and we are getting 205.54 and so on, right? So M13 was, okay, so you can get these positions from that, and you can transform to galactic. So you can use position of M13, transform to galactic. And in a very simple way, it converts uh, uh, from RA deck to the galactic longitude latitude. Yeah, 59 and 41. Okay, so these are, yeah, similarly you can transform to, yeah, the same thing. Okay, so position of galactic, and you can, if you say position crab dot ICRS, that is in terms of RA and declination, International Celestial Reference System, which is RA index, you can convert from galactic to RA deck, right? So it's as simple as that. Otherwise, you would require a lot of work for converting from one to the other. So in your computations, depending on which system you are required, this becomes very helpful in all your computations. Okay. Yeah. So similarly, you can say position crab dot data dot longitude, it is giving you the longitude, and latitude, it is giving you the latitude. So you are getting it in terms of hour angles also. Okay. So then if suppose you have um, finding distances between positions in space. So you have some position of, yeah, position Sagittarius A is 0, 0 in the galactic reference, right? Sagittarius A is where the center of a galaxy is. So this is its position is 0, 0. And if you see the separation, it is giving you, yes, well, yeah, position of crab we have, yeah. Similarly, you can have conversions to the Earth's alt-azimuth system, where you have from astropy coordinates import Earth location and alt-azimuth system, right? So whenever you use alt-azimuth, it's very important to even know what is the location, because it's a very local thing, and the time, yeah. And from astropy time, import time, and import data time. So I'm importing all these three. And so, for example, San Jose, where this conference is being held, I use the Earth location function from AstroPy coordinates. Yeah, I've imported this Earth location, and I'm using Earth location and saying latitude is, so if I know the latitude and longitude of this place, San Jose, which is, I think, minus 27. It is in the southern hemisphere, 27.58 south and 48.6 west. So since it's in the west of Greenwich meridian, you are putting minus, and you are putting minus for the southern hemisphere. And uh, we print the geodesic of that, and it's telling what is the longitude, latitude, and what is the height in meters. Okay. So for the, so it has all the data of the globe, and from it, it's showing that this is the longitude, latitude of the place. And okay, and now I can use this time underscore UTC, time now. If I run this command anytime, it will give me what is the time, Greenwich Mean Time at this moment. So it is 15th of October 2025, and it is 18 hours 52 minutes in Greenwich, the US, right? Greenwich Mean Time. And if I want to convert it to the Brazil time, we know it is minus, what is the Greenwich Mean Time? Minus 3 hours, and I'm converting it, and I can see the current time is 15 hours, 52 minutes, and so many seconds, and so on. Okay, so similarly, we can do it for so we can find, okay, so I have a spelling mistake here. Yes. SAO. This is what I was, yeah. So this should have gone by fine. Earth location is this, and not now. We have to put this time here. I have to put this one here, and it will print the Krebs azimuth. Yeah. So this is what it will do. It's still running, but it will give the alt azimuth at the location wherever you are. So wherever you are working from, you have to find the Earth location and run this and find the time, local time then, and calculate and run it. So it's taking a while to run. Okay. So just make changes in the file I've sent. It was marked for some other location, Mathura, but you better change it to Sao Jose. Okay. Just be consistent with this spelling which we have here and put the same here. And the time also, uh, Sao Jose time, this is how I've written. Okay, I'll stop this from running because it seems to be taking a lot of time computing. Oh God. Okay, now coming to the tables. Uh, you can handle VO tables and all from AstroPi. So from AstroPi tables, import table, and you can print table. At the moment that there's an empty table, but now I'm creating a table with source names Crab, Sagittarius A, Cass A, and Vera Junior. And when I run it, we are getting the table, right? So similarly, if you have VO tables which you have downloaded from a Gaia site or wherever archival site, they should be able to read and handle tables in the format. And then you can access table columns, you can access one specific one, and so on and so forth. So this is simple. Anybody who knows Python knows it's the same format and it goes on. So I'll be giving it to you. And similarly, here's how you can you can write to in FITS format FITS. You write these files. Okay. So now coming to FITS images. So FITS stands for Flexible Image Transport System, and it's a standard which is being used for distributing astronomy images, tables, spectra, all the data through this FITS format. And so from AstroPy input output, yeah, astropy.io input output, we import FITS. This is okay. And then we use fits.open to read the FITS file. Okay. So we have the FITS file sitting there. The name of that is CASA. Yeah, it shows you in which band it is. I've shared it with you. And then you can see the header information. So the FITS files, they come with image and header information. So you HDU list. So HDU list is space open list. And when we are looking at the information, it says number 0 is primary, one primary HDU, 26 cards. The dimension is 1024, 1024. And yeah, so it is a 1K by 1K format pixel. So HDUL primary, or you can use it image. HDU is HDU list primary. Either you can use this term primary in inverted commas or 0. The number is 0. So you can read HDU list 1 or 0 or specify primary or whatever. Okay. And when you look at the data, you see that it is a set of numbers, right? So image in a astronomical image is essentially a matrix. It's a row and columns of pixel elements where it has recorded certain counts of photons which has come in. So here you see mostly it appears to be 0, 0, 0, 1, 1, 1. 0, 0, 0 because it's showing the upper one, there's no light in that. Okay. So I'm reading this, and then I'm I have to, this will give me an error because I have to rerun. I had stopped the kernel. Yeah, I'd have to rerun this matplotlib, and these things I had to, yeah, I think everything will be fine. Yeah, so this is it. And now when I plot it, I can see that there are different color maps. So I'm using the Inferno one, and this is giving us uh, the supernova remnant gas, Cassiopeia, right? So this is an image. So what we are seeing here is the primary one, or the number 0 header unit, contains a 1024 1K by 1K file. So if you read it as a data, if you just read the data of it, you read it as numbers. But using matplotlib, we can plot it by using PLT. Yeah, we have imported matplotlib.pyplot as PLT, and I'm saying plt.imshow, the header unit, which is data, and the lower, we fix up what levels we can do it in Inferno, and we are also plotting the color bar. So this color bar is showing the intensity. With 0, it is this color, and 100, it is slightly purplish orange, and 200 is okay. So this is how you handle, and uh, so if you see it in different color maps now, for example, I am using magma. This was in Inferno, this is in magma, and I can pick different ranges and see it. If you say image HDU header information, it will give you the header information of the whole thing, where it shows that it is Cassiopeia A. The date of observation was or this 12 December 2007, 5th December 2007, at what time, and the end date was what time, right? How many hours exposure, and the header information gives all kinds of details of the thing. Okay, so with this, yeah, so from AstroPy world coordinate system, we can also look at the various things in it and see the RA and declination of the object, and you can read the things from the sky and do it. So this is one way of reading FITS files, because if you have a FITS file, which I will just show, uh, I'll just share. I'll share my whole screen, entire screen. Okay. Yeah. So let me close this. Yeah. So suppose I have one. Yeah. This is the FITS file. I hope you can see it. This is the file which we're looking at. So you cannot see it by using any of these uh, game for Acrobat. You require only specific ones. For example, DS9 is also used to see that, or you can see it in Aladdin. So they should be. So the DS9 is opening up. It's taking a while. So these FITS files, you can either see it in DS9 through IRAF, or you can use it through File, Open. Yeah, so you see that in DS9, and you can see in different scales the color maps. Okay, this is at Cassiopeia. Similarly, through Jupyter Notebook, we could see it in different maps, and this is what it shows. And you can see the header information from here. And the same thing which we read it from otherwise. Okay, so there are different slices in this. So one gives the header information, the time. This is what we had seen, right? the object name is so and so, what is the size, axis length, 1024, 1024, and so on and so forth. Okay. Again, DS9, you can do other work along with this. Yeah. So with this, I will stop my session, and Priya ma'am will continue with Priya. So if there are any questions you can ask, otherwise what you have learned in these sessions will be used to access Gaia data and to do various things. Okay.
Yeah, so thank you. I'll continue now. And basically, what I'm going to show you now is what we actually did with TopCat. If you remember, when we tried to identify the members of the cluster M45, right, using TopCat, I would now like to show that to you. How would you do that using a Jupyter notebook? Okay, because finally, when it comes to publication, like Alessandro, I told you, you'd start off by using it with TopCat and stuff like that. But then finally, when it comes to doing serious work where you're actually going to publish it and getting it to a serious form, that's when you would actually require to put it in the form of a Jupyter notebook and do much more careful analysis of the problem. So I'll show you what do I mean by careful analysis, and when you see it, you will be able to realize what exactly is it that I'm talking about in terms of careful analysis. Right? So, okay, I'll share this one also with you. 1 second. I'll just I'll download this file, and the thing is that 1 minute. I'll just download it. Just give me a minute. So I'll just take it. Gratitude. I'll just put it as gratitude. Okay. So I'm going to share it here on this thing. So what you can do, the safest thing to do is, if you don't want to install any software, right? Then the safest thing to do at any point of time is to just open Google Colab, right? So that's how even I'm also gonna run the notebook directly through Google Colab. Where is my back to the meeting? I can't get back to the meeting. Okay, 1 minute. I'll stop the share now. Then I'll be able to do that. So, where is this attach wala button? Where's this attach? I want to message everyone. Attach is which one?
What?
Attach button. There's one attach button, no?
इसमें पोस्ट कर दो तो
I want to attach. How do I?
शेयर होना है
No, I want to. There's an attach button that is there.
इस फाइल
Where? Here. That's what I was asking. What? 1 minute. I'm sorry. I just check. How did I exactly download it? I downloaded it as Gratitude. Okay, capital TOT. Okay. So here it is. Yeah. So all of you all have shared this. have shared this Gaia Tute, and you can open it with a Google Colab file. So if you ideally do it along with me, I think that will be most beneficial for you, because you will see how it basically runs, right? So now I can't do Kepler and I can't do. Okay. Fine. So I hope now you can see my screen, and most of you all should be able to even open it yourselves and see it, right? So actually here, just for this thing, there's a little bit about the Gaia Space Observatory. It was launched in 2013, and it's, okay, I should actually edit it, expected to operate around 2025, and in January 2025, that was when Gaia took its last science observations, and then finally it is what is called, it was passivized, in the sense it was sent into what is called a retirement orbit. So it's basically they empty all the fuel from the spacecraft and kind of put it away, because by then all the the stuff which they had, the propellants etc. were all over. So ideally this was a mission launched in 2013. It went all the way to L2, and therefore it took a year for that. And then from 2014 it started observing. In principle it was a 5-year project, only till 2019. But then since it was also going so well, they gave it a 5-year extension, and rather more than 5 years, because it worked till 2025. The spacecraft, like we mentioned earlier, this basically is an ideal source because it gives you astrometry. It measures the positions, distances, and motions of stars with unprecedented precision. And the application of this comes in almost every field. It could be even if you're studying some near-Earth objects, asteroids or planetary things, or stars or galaxies or quasars, or there are all kinds of objects, even black holes that have been observed using them, because you are measuring the velocity of stars. So obviously stars in the vicinity of black holes are going to behave differently. So you can actually catch them even with the Gaia data. Right? So that's been done. So what I was showing you was a simple exercise, was about this thing, that we won't go into these details. But like I told you, this measures parallax, radial velocities, and positions, and then various Gaia releases. So I'm going to show you yet another method. If you remember, Alessandro showed you some method of querying Gaia data, that is using ADQL, which is the astronomy query data query language, which is very similar to MySQL. I also showed you how could you download the data using Topcat itself. Now I'll show you yet two more ways. This is the way of downloading it from your Jupyter notebook itself. You can access the website, right? So this is the Gaia website, and from the website itself, you can download the data. So what we are doing is, here from this Jupyter notebook, we are accessing the Gaia website, which is the ESA, European Space Agency website, and from that itself, we are going to download the data, right? So you can do that also, and from that website, you can actually download it using two methods. You could download it either using what I'll show you, a command-driven thing, or in this place, you can also use the ADQL, so the Astronomy Query Data Language, exactly like you were shown earlier. So you can actually put in the syntax for that, and accordingly also download data using that technique. I don't know what's happened to the website. Why is it not going on to that? What happened? Just check. Now my net seems to be working fine. It's still loading. Yeah. Okay, we'll just move and I'll come back. Okay, great. So this is the Gaia website, the ESA Gaia website. And from here, this is one of the simplest ways also. This is, you can go in for a search. So the simplest way is that you can give your thing. You can say, I want to search M45. Again, Simbad takes the trouble of resolving it and gets it to you, right? Now what Simbad would do is you can decide whether your target is in a circle or in a box. And you can decide the size of the radius in which you want to query it. For example, you want to do it in whatever. Remember we did 30, I think, arc minutes. So anyway, you decide the size of the cone radius which you have, exactly like we did it in TopCat, and you can decide whether you want a cone or whether you want it as a box, right? You can also choose your data set. For example, there are various data sets over here. This is the Gaia data set. This is Gaia's source light, which you already had a look at, and then there are many more. This is the EDR3, early data release 3, but there are also other combined other data sets which are derived from the DR3, and you can have a look at what of this. The universe model is a simulation set of the data set, and DR2, etc., earlier releases. So you can choose whichever release you want or whatever this thing you want. Now with this you have extra conditions also, in the sense you could, you have columns, there are various columns. You remember we were talking about columns, how with ADQL you can specify which columns do you want. This is exactly doing that. Or you, like I told you in TopCat, by default a certain set of columns get selected. Over here what happens is you can actually tick on which are the ones you want. So by default you have RA, you have DEC, and you have proper motion deck. There is proper motion RA. This is the RA. Here's the deck. Proper motion RA, proper motion deck. Then this is the Rouvet factor. Then the BP minus RP and various other factors. So there are a whole bunch of columns. So you can actually choose the ones that you want, and then you can submit a query. So you can do this, and you can submit a query, and you can also say which is the format in which you want your result to be there if you want to download the results. There are various formats. When we showed you TopCat, I didn't get the time to show you that catalog data can be in various formats. There's a special format for the virtual observatory, which is called the virtual observatory table format. Okay, so that's a VOT format, virtual. There's the CSV, which you also had a look at, which is the commands separated variable types. There's what is called the FITS types. There's a JSON. There are various types depending upon the need you have. And now here is your data set, right, which you see we queried and we got it, and that's how you can download it. So you can download the result from here. If you want, you can also go into the advanced ADQL, and the advanced ADQL, you'll put up your query exactly like you were shown by Alessandro, where you actually write select from where. That is the basic construction of SQL. So you select whatever you want, object with RADEC or whatever you want, and then you say from which is the database from which you are selecting it, and then where are the conditions you do. For example, you say your parallax should be non-zero, greater than 0, or whatever you want it to be. You can fix up that to be your conditions, right? So that can come over here. It could have even come in that earlier file where there was place to add the conditions, right? And then what has been done to help you, there are a certain amount of data sets which are actually, there are a certain amount of queries which are put up over here as example queries, and you can actually use that to find it. So you can, it can even give you the corresponding thing for your basic query and tell you what that is, or you could do it for single objects if you want, etc. So that's how you can actually query all the data set from the website, right? So what we are here doing is our Jupyter Notebook is being used to query the website. Now these are the standard libraries which we need with Jupyter Notebooks: NumPy, Pandas, Matplotlib, Seaborn. We also take Astro Query, because now I'm going to show you yet another query which is being done again with your Jupyter Notebook. If you do not want to go to the website, then you can directly use what is called, when you did Astro Pi, there is a section in that called Astro Query, which is used to query the data. So you can actually use Astro Query. So here we pip install Astro Query, and you can actually look at these to actually see what can you do in that. So now this is the code. That is why I've shared the notebooks to you, because if you sit and type it out, you obviously may make mistakes in punctuation and various other things, due to which your code will not work. So it's obviously safest to actually type out the query. Often in today's times, even ChatGPT is pretty good at writing out the queries, or even in Collab, you can use Gemini AI. So I hope you are aware that, for example, if I put this, if I open a code cell, you can always say generate with AI, and with generate with AI, you can actually write a thing, say for example, query the Gaia database, right? So for the nearest 100 stars, right? So what Collab is doing is it uses Gemini AI, and Gemini AI basically generates the code required for it. Now, obviously, not every time does Gemini AI do a good time. For example, Gemini AI says, now I ran into a word, could you try again? Or so I had never tried this thing out again, how well it does it, but I can for the, let me say, query this thing for the data of M45. Let me just see whether it can do that. And so sometimes ChatGPT gives you a good result, sometimes Gemini AI does a good job, and sometimes neither of them do a good job. So here you can see it's basically done one with ADQL, where it is actually querying this thing for Pleiades data. It's giving you a center, radius, it's exactly giving you what I'm going to be showing you, which is then over here. You can see this over here, that it's exactly the same code. Have a look at it. We are saying query Isagaya base for Pleiades data. So what do you say? The center is chi quad. Now you know what this means because you already had your AstroPi session. So sky coordinate, these are the coordinates of the Pleiades. Pleiades is M45, which we were talking about when we did the top cap thing. So your RA is given here and your deck. If you see u dot degree means the units are in degree. And I'm looking for a radius now of 2 degrees. Okay. So here is the choice of the columns I want. I want RA deck, parallax, PM RA, PM deck for G magnitude, BP minus RE. So now here is the code from select from where. So select is this, from this is the database, where is what are the points, which contains the points, this thing, in a circle which has a radius of 2, this thing, and it's looking for it in that. Okay. And what are the conditions we are putting? Parallax should be greater than 0, G magnitude is not null, and BP minus RP is also not null. We want it only to be done for stars for which we actually have a G band magnitude as well as a positive parallax and a colored term, right? Because we want BP minus RP is also not null. So you can run this code, right? It looks safe enough. Run it and you know your results are now and get this thing. So here is your thing, but you see there seems to be a problem. Rho has no attitude. But I have already done it over here, and let us just compare. We said select, let me run this. This was running fine. This is the code that I had given you. Yeah, I don't remember what is it that I corrected, but in short, I think ChatGPT did make some mistake in this. I don't remember what are the mistakes, but I'll just delete it and we'll proceed ahead. This is the code which you have in the file I've given you. I hope you're all managing to open that file and see it. So here you see this is my code, and here I've downloaded this thing. So I've got this data. This is the data file, if you can see. Data is the results to pandas. So I'm already converting this into a pandas data frame, right? Otherwise it will be a NumPy array. So what I basically want is that pandas data frames is the best way to do data analysis in general. So it's always good to convert your data to a pandas data frame. That is the thing that you should blindly do. Okay. So here let's say we've converted it. Now if I type data, I can see that this data file is a pandas data frame, right? And here if you can see, I've actually listed the file data, which is the source ID, RA deck, parallax, PM RA, PM deck for G magnitude, BP minus RB. These are the columns, if you remember, these are the columns which we asked for, right? Here, these are the columns which we asked for, and hence that's the data which is coming up over here. Okay. Now, this is yet another thing is supposing you had downloaded the data, say from the data set, you could even do a PD read CSV. We are not going to do this now because I have actually got the data from, it's already there, right, which is my data file. So I won't be doing this, I won't. But in principle, I've just kept this so that if you run this now, this is going to show you an error because it will say it doesn't know where this file is. Let's run it. It's going to tell you that I don't know where m45 all.csv because we don't have such a file, right? So ideally, we should give it a file, but we are not doing it because we've queried it and we've got this thing. So now what have I done is I'm calling this file all stars. My remaining code, all of them is for a data set called all stars. And therefore I'm calling my data to be all stars, okay? So that's just something I'm doing for convenience. And now here you can see I'm making a plot of array deck for all my stars. This is exactly the kind of plot which we did for TopCat, right? So in TopCat we got an array deck plot and we plotted that over here, and that's the thing. Now the next question comes, if we now plot the HR diagram of these stars, you can see that this plot is a total mess. If you remember, these were the members, which we'll get out separately, and this was the other stars. So if we plot it all together, we get it all like this, which is quite a mess. So now we need to clean this HR diagram so that we remove all the background and the foreground stars, and we end up with only the cluster members. So now here we will do the plot which we did earlier, which is we are plotting proper motion of array and proper motion of deck. If you remember these stars which I told you, which are centered near 0, 0, these guys are not cluster members, while these stars are actually cluster members, right? Which are centered something around 20 in the RA, PM array, and something like 45 in PM deck. So these are the stars which make up our cluster, not these. The bulk of the stars are what we call field stars. The background, foreground stars are called field stars. So the stars of our interest are these, not these. Okay. So what do I do if I even make a plot of proper motion of RA versus parallax? You can see again, I have this bundling of stars. Proper motion RA we know is 20, and we know that for this cluster, remember if you know, we saw the parallax was like 7.3, right? 7.36. So that's it. That's the clump we are interested in. Similarly, I can do one of proper motion deck and parallax. I know that my proper motion in deck is about, here it's about minus 45, so these stars, and the parallax is 7 point something, 7.36, so it's here. So now what do I do? If I make a plot of histogram of parallax, remember we did such a plot, we basically got two peaks. There was one peak close to 0 and one peak close to 7.3. These guys are our cluster stars, while these are the field stars, which we do not want. So this was just data exploration. Now what we do is, again, we can make a plot like this of RA. We are getting 2 bumps. Similarly, if we make a plot of PM, of deck also, not even PM deck, again we get 2 bumps. This is PM deck, again we're getting 2 bumps. So now here what I can do is I can use, you were shown pandas that you can actually ask it to make a profile to tell you everything about the data set, because always before you do some analysis, it is good to study your data set, right? See what kind of a data set you have. So for example, for all these parameters which we have over here, it's telling us the count, how many objects do we have, what's the mean value, what is the standard deviation, what's the minimum, and then these are the quartiles. The 25% quartile, the 50% quartile, 75% quartile. So you have all these quartiles mentioned over here in this. So you can basically, the idea of this is basically for you to look for outliers, right? Do you have some strange stars which are falling into your data set, which are, kind of spoiling the data that you're getting, or, creating some kind of problems. So that is this thing. You can also plot it in the form of this thing. Okay. Now the deal, so here we have our D types and all that. Now how do we identify our stars? So here what we did is we actually defined something called a mask, right? So if you remember, our data frame is called all stars, right? And we have different columns in that called parallax, PM array, PM deck, etc. So what do you do in a mask? You actually put some cutoffs, right? So if you remember the parallax slide between 7.3 or something like that. So here I've put a rough cutoff where I'm saying that we know we want value 7.3 something. So we're saying we're taking parallax greater than 6 and less than 8.5. Again, remember we made the histogram here, so we can see the one we made for parallax. So we've said more than 6 and less than 8.5, right? 6 and 8.5. And we are saying here are our cluster members. So to make our mask, we are using 6 and 8.5. Then again, we look at proper motion and deck. We've taken 30 and 10. So let us scroll up and see. This is our proper motion, in RA, We've taken 10 and we've taken 30. Obviously 30 is fine, but here obviously there would be some of them coming from here if we are taking 10. But we've taken 10 and we've taken this, but it's with an and also. So hopefully then other things should go. Similarly, deck, if you remember it was minus 45, so we've taken minus 50, minus 40. So you use this to define your mask, and then you say members are all sky mask. That is all sky rows which satisfy the conditions of mask. So we have made it go through this condition of mask is going to be our members, right? So if you remember when we did TopCat, we actually roughly drew out the mask. I mean, the mask was, remember when I marked the subset, we kind of marked the stars which are to be the members, right? But in this case, what we are doing is we actually define it using numbers, right? So ideally speaking, what happens is, supposing if I were to fit Gaussians onto this, right? I can fit a Gaussian to this, find out the standard deviation, and accordingly decide the range. Here I've taken minus 40 to minus 50, but I can kind of, you see in PM deck it's not a big problem, but for example in PM RA, we took 10 to 30, but you can see that here there are many stars over here in this. So ideally speaking, had I fit this to a Gaussian and then got the value of my standard deviation, then I would have accordingly selected my, my members, and accordingly be able to cut it off. So if you remember when we got the profile, we actually did get our values for the standard deviations, right? So for example, if you look for proper motion of RA, you can clearly see the mean value is 3.21, right? And this was my mean value, but this mean value is bad. Why? Because mean value includes all the stars, right? So ideally speaking, I should be doing not an all stars describe, but I should be doing something like this. Let me look at this. When we did members was this. We did members describe. So this is the one. So here when you see, we've taken parallax. Ideally speaking, you could have taken it with all this thing. So the mean value was 7.36, which we had got, and the standard deviation is this. So you have 7.36. If you want, you can take 3 sigma, 5 sigma, whatever you opt to do. Similarly, when you're looking at this guy, which is the PMRA, for example, there's PMRA, proper motion. Okay, it's got rubbed over here. But in short, you can actually use it to find out what is the value of the mean and what is the value of the proper motion, right? So now what happens now that we've defined the members, if you look at the histogram plot, this is the histogram plot for this thing. Here are our members. And now here, once again, I'll show you the beautiful plot which we got with TopCat 2, where here, these orange stars, if you see, the orange stars you see are the member stars, and the blue stars are, you see, the background. Now you can see there are some orange stars over here. So these are obviously contaminants. They have to be removed. And when you do further analysis of this thing, you can actually remove the contaminants. But otherwise here we have what is called our clean HR diagram. So now here if you plotted it just for the members, this is almost exactly the plot which we got when we ran TopCat to get the members. If you remember, it was nice and clean on the top over here for bright stars. But when we came to faint stars, you have a larger scatter, basically because the scatter you are wrongly identifying, there are errors in taking these guys as members because they are fainter elements. Right? So you can make another mask. Maybe you can make a much more nicer mask This is a mask on the quality check, okay? This is giving an error because we've not downloaded this stuff, the parallax of an error, but there's another column in Gaia which says the parallax of an error, which is like a signal by noise. So it was mentioned earlier also by Alessandro. So if you're taking it greater than or equal to 3, you're taking a 3 times signal by noise. So here this is what is called a quality check, because we think that some of these stars are in here because in spite of their quality, the data quality be bad. So when we do analysis, one good step is to actually throw out all data which is bad. So here we had a second mask where you're taking it, you're choosing this over error. This is the PMRA over error, PMDEC over error, Rouve factor, etc. And this will not run because we have another data file. But when this was run, we got a slightly better one, right? So now you want to take over. So here I actually showed you how you could use this. You can further play around with it and see how you could improve this HR diagram, get a clearer diagram. There's a little bit of an exercise also, which I've added over here. There's more about ADQL, but I think you were kind of introduced to it. Select from where. So for example, you could also choose the closest 100 stars, which is there, and you could actually plot an HRD for few given clusters with the titles we are giving you, the names of these clusters, and you can actually see if you can plot their HR diagrams, right? So I'll stop with this HR diagram, and I'll be happy to first take questions. I have another exercise which is there on using Kepler data, but I do not know whether we actually have the time to do that. So
Yeah, okay. Five.
yeah, but we got to stop at 1. In 20 minutes, I've got to stop. But till then, let me just ask: does anyone have questions, or did you all manage to run this notebook? Did this work fine? I did not show you, but you can also access virtual observatory tools. For example, you can even access Aladdin from a Jupyter notebook, in the sense, just like we went to the website where you saw the Gaia data could be queried from the ESA site. Similarly, there you can also go to the site which houses Aladdin, so that you can actually access Aladdin from the Jupyter notebook. So that if you remember, what we did is we later on plotted all our stars onto the Aladdin image of M45. So similarly, you can even do that in your Jupyter notebook, where you could display M45 and then overlay the stars which, the ones which you identified as members, onto the image of M45 in your notebook, right? In your Jupyter notebook. It doesn't have to be only, because you will want that to be preserved and kept so that you can actually see it whenever you want to, right? So a lot of these VO tools, you can kind of access it from this thing. And kind of talk between these different tools. So let us first, I'll just give you all a short while to tell me if you all have questions. Please let me know if you all have questions about what we did. You want me to do Kepler? You want me to do Kepler? In 20 minutes, can I do that? Yeah. Shanshan, okay. You want to say something?
No, just
We can't hear you. You are muted.
yeah, it's okay. Just waiting for if anyone have some questions, and
Yeah, I think after
because
we've
we
done so
have
much, there should be lots of questions. No, most of them are saying, I don't see. Let me check the YouTube page.
thinking that because most of our training today is about the real.
See, let me check the YouTube. Sorry? Yeah, sorry. No, I was taking the YouTube page, and that's how that came in. Yeah. Okay, go on. Sorry.
Um, I'm just thinking that because all the training today is about the VO and the data and how to use the VO tools, we didn't go much on the AI things.
Yeah, that's right. That's right. So, would you
Yeah.
like to add on that, Shanshan?
Yeah, I mean, it's the last session, last part
Yeah.
is about the discussion. And I think maybe we can see if, because we didn't talk much about the AI, so maybe
Yeah.
we can see if our people have some questions about the AIs, so we can have some simple chat about discussion about this.
Yeah, yeah,
And
sure. Sure, sure, sure. So, so participants, you all are most welcome to, yeah, actually panel discussion is after 20 minutes, but we can start it now. Or if you want, we can cover some other things. Shanshan, would you like to cover something about AIML or something like that?
Uh, I mean, it's I don't want to go very rush to
That's right.
the
That's even my worry. Yeah.
we didn't give much materials to talk about, so I just want to see maybe participants have their
Mhm.
or their questions about how to use this data and how to what they want to do with the AI machine learning these things. Yeah, so we can talk. Yeah.
Sure. Yeah. You want to say something? Participants, anything? I think there were some questions earlier. Yeah.
Virtual observatories are fine, but virtual sessions are not very encouraging. We don't know the feedback. We don't understand how much have the participants gathered, if they have any doubts. So they have to speak up so that we know what has to be covered up. We'll share the material which we have done, the Jupyter notebooks and some write-up on what was done. But it's important to know whether they have followed and how much have they followed.
I think they are quiet.
Yeah, it's maybe because it's all online training. Some at some areas around the world it's pretty late, so.
So what do we do with the panel discussion? So Sunshine, since
So
we have done so much of
shared
talking,
the
is there
Jupyter
stuff you want to
notebook.
say?
So maybe the participants should try them out later. And if they have issues, they can always write to us. And if required, we can have series of sessions on weekends or so, where we do one aspect at a time. This was a overall view. They got a very big understanding of what can be done with VO, and but for them to feel confident of doing, if we can consolidate a smaller group if required, and we can have many sessions with them on an appropriate time and date.
So Shanshan, since we've done so much of the talking, do you want to say something? Because you just had the half an hour slot. You want to add something?
Yeah,
You have time.
I'm not sure. I want to.
Ah, okay. Yeah. So I think you have all the Jupyter notebooks, right, Harshit? I shared the Gaia one, and Sir shared you his notebooks, right?
The
Yeah, we can put it on a Google Drive also. Yeah, that's not a problem. We can put it and mail you.
And Harshit, you can use these files and adapt it for other objects which you are interested in studying. So this is, these are templates, how to read, how to, write them into files or how to access. So you can always modify these things for something else which you want to do, for some other object, some other, database or. Simbalan.
Maybe you can come.
I think
Okay.
maybe I can see that
Something.
our last session is
Shanshid, we can't hear you.
hi, can you hear me?
I'm muted.
Yeah.
Okay. I'm
Yeah.
muted here.
The last session is the challenges in AI astronomy and data analysis. So if the participants don't have their questions, and we have go through so many things today because all the materials and all the Python skills, and I think they need time to learn and to practice their own. So we can maybe open to for them to later email us and to contact us and to see if we have some more discussion. Yeah.
Yeah, definitely. That's a good idea. Yeah.
Question.
Yes, AI.
Okay. Oh. So Harshit has a question. Using AI in gravitational wave astronomical data. Definitely, it is being used for grav wave data. Again, the technique which I was telling you about, template fitting, right, which is used for variable stars. Similarly, you have different templates for noise and other sources, which you have to basically cut off from your signal. And, it is definitely, it is a job of AI only, which is done for gravitational wave, this thing. If you want to add something. Yeah, okay. Oops. Yeah, any more questions? Yes, you could. I can share. You can share it if you want. So if you, I was just Googling on this thing, AI and grav wave detection. You can see it's definitely very much used. You'll find a lot of articles over here. There's a talk on machine learning, grav wave stuff, and there is plenty. You just need to look around and find. Yeah.
Nice. Glitches detection and classification, US regulations involved. Yeah, AI is being used for exoplanet detection too, because if these are eclipsing, the detection by uh, the variability of the light curves of the stars, so the AI can very easily match the curves and find out what kind of a planet is orbiting it, get all the parameters and so on. So, yeah. Because there are over 6,000 confirmed candidates of exoplanets, and we have light curves of many, and AI can be used very effectively to look at the light curves of these orbiting planets, the dip in the wave, in the light intensity. So it can be used really effectively, and it is being used too.
Yeah.
Then Ashok says, how often is AI currently used in astronomy research? This doesn't only align to analyzing data, but also writing codes, I'm asking. Is it used openly currently, and should I concentrate on skills and understanding how to code work rather than mugging up syntax, unlike the conventional way? Yes, so yeah, of course, AI is being used a lot. You see, the whole discussion which we have been having since morning is astronomy has become a data-rich science. And when there is tremendous amount of data flowing in, it becomes essential to use machines to understand it. You have to use some computer language to study it or use machines to understand because there are billions of records and tremendous amount of data. And AI can be used very effectively to see patterns in this. And it is being used. It is being used in all uh, aspects of astronomical research. May it be morphology of galaxies or you are trying to find the classification of stellar spectra or membership determination of star clusters. It is being used almost everywhere because we have so much of data. Not humans are not in a position to sift through this large amounts of data. Um, so machines, if they are trained well, they can do a good job in a more efficient way.
Yeah, and about the coding bit,
Your Mac, Priya.
Yeah, in the case of coding, obviously, in today's time, there is so much of AI in coding. Also, for example, if you're using Colab, you'll use Gemini AI. If you use GitHub, you'll use Copilot. If you're definitely, or you could just be using ChatGPT or DeepSeek or something like that. So actually at least I personally do not think it's a crime to be using AI to write code, because it's anyway often, most of the time you have to alter the code that you get. AI generates it's a good start off of what it does, but then often your prompt may not be. So finally, even if AI generates the code for you, you do need to understand what that code is, so that you slightly again tailor it for what you want, because what you want may be slightly different. So I think that there is, in today's time, it's like it's something like I don't know, but when say calculators came in, people probably thought that people will stop calculating because calculators have come in. But if you know that you do end up calculating in your mind also sometimes, it's not that you're only using the calculator. Similarly, these tools are there, you will definitely use them for coding, but finally you will have to do it on your own also, like it's coming in all other fields. So I think there's nothing wrong if you're using it, but you have to be, actually it puts you at a higher level, because you need to be able to critically assess a code that is given to you, so that you can say whether it's good or bad, or what has to be changed in it. So it's good that you don't have to waste your time thinking of syntax. You need to worry more about the algorithms. So for example, you can ask ChatGPT, "Okay, plot a straight line with values of X and Y." That's no big deal. But then you may later on figure out about how are you doing the fitting process, or what is the algorithm you're using, and things like that. So do that, and that's a good idea to, I think it's a combination of both. You'll be using the tools as well as your own brain to together write your code. So that's fine. And I think that's the modern way of writing code. It's like the modern way we do our spellings, or we write things, or do calculations. So it's fine. Yeah. Shanshan, what do you have to say about how good or bad is it to be using AI?
I think I think people I know in China who studying astronomy, pretty much everybody use the AI right now. I mean the LLM, and also the back to maybe a few years ago, with doing the machine learning. It's because AI include a lot of things. The back a few years, we do the machine learning, and we write code ourselves. But right now, if you are doing machine learning to train, it's really fast if you use with the LLM help. Especially nowadays, there is like a cursor, this vibe coding things, and it can help a lot. Yeah, and there's other things that people are using AI for, is like writing papers, actually. Yeah, because in I'm not sure in other countries, but for Chinese people, because we have translation problems, so there's a lot of students are using AI at least for translation. Yeah, and it's really hard for teachers to tell if they are using this right or wrong or properly. Yeah, but
But are there some softwares, plagiarism check softwares, which can actually check?
yeah, it can check, but
Okay.
it's getting harder. Yeah.
Rafael and Alessandro, you want to say something?
We were just talking during lunch that the problem with AI is that it's inevitable. We can't just not use it. But students must be taught how to use it effectively and responsibly. then I think that's a major challenge. But when I look back, that was the major challenge with Wikipedia and with Google and with the internet and with probably calculators. For those that are old enough, you are not supposed to use calculators. And anyway, the question is that education is a continuous process. So now we have this new, amazing, and very faulty tool that must help the students to learn how to do the best of that. I read an article that say that when Steve Jobs was thinking about computers, personal computers, he said that a personal computer was going to be a bicycle for the mind. Then you have to learn how to ride it. And it's going to be better than walking, but you need to learn how to ride the bicycle. And the author of this article was saying that artificial intelligence is the flying car of the mind. That if you don't use that, if you don't learn how to use that and effectively and safely, you're going to crash and burn. That was very interesting. So that's just my take on that. Thank you.
Okay. Alessandra.
I was in a round table about the ethical use of AI a couple of weeks ago. So yeah, the use of AI has been on my head a lot lately, and I think what possibly one of the most interesting and the most discussed things is what Shanshan just commented about the paper writing. Up to what point what you write with the help of an AI is actually yours and not. So I think at the end of the day, there's some consensus that if you write and then you ask the AI to help with grammar, with rephrasing in better English, that is a good and acceptable way of using it. And obviously, if you go like, okay, so just now write for me this, and then I copy and paste, that is, I guess everybody agrees that that is not an ethical use of AI. And I guess at the end, this is a tool, right? So and basically we use it for a lot of things. We use it for writing, we use it for coding, we use it for brainstorming, which is something that perhaps I don't think it has come up yet, but we actually use it to exchange ideas. Maybe you don't always have a colleague who's awake at 11 p.m.
Yeah, yes. Sometimes you just chat with the.
And sometimes you just want to chat with someone. You just had an idea, and you just want to chat with someone, and you just start saying, "I just had this idea. Does it make sense?" And
It's a thinking process.
Yeah.
More like.
it's a thinking partner.
Yeah.
And in some cases, it can be an interesting thinking partner. Again, it sort of depends on the model. There are some models which are a bit too friendly, and there are some models which are less friendly. Also, again, you can ask the model to be more or less friendly, and more constructive or less constructive. It's actually so much fun. But it's basically a new way to do research. There's one sentence that my wife says that I wrote something ago that was like, having an AI is like having a research partner with infinite patience, available 24/7, and doesn't judge you. And that is fantastic, right? Because sometimes you go like, I may not say this because maybe this idea is a little. People are going to say that there is a silly idea or it's an obsolete idea. The LLM will not judge you for having said, what if the sun rotates around the Earth? but whereas a colleague would certainly judge. So it is a new way of approaching science.
Yeah, it's without a doubt, it's a great tool, and it should be used as a tool with caution. And the ethical or unethical part is obvious. You yourself realize when you are going wrong. So the ethical and the moral aspect finally depends on the individual. Because even without AI, if people want to be unethical, they can be, and they do it. They plagiarize somebody else's work or not give credit to the right people. So that ethical issues remain with human beings, and it's not the AI which can make changes to that. And one has to be kind of checked it out that in certain cases, the DeepSeek or Chat GPT, sometimes they're extremely good, but there are times when they absolutely go wrong. And one has to be using them with a lot of caution. Uh, and and yes, it's a tool which is required for research today, and there's no going back. We have to change with times. And about AI not judging you presently, probably present systems are so they may evolve themselves and start telling you that you are going. I mean, they may have their own judgments over what you are chatting with the bot later. You never know it. He could be your like a other wife who would be nagging you and saying, "What are you doing this for?"
Mhm.
Yeah, I think also it's important to learn how to use AI properly because I have seen the questions from the participants that mentioned for the AI do the simulation, Monte Carlo, this
Yeah.
kind of. I think if you just put all these keywords into the ChatGPT,
Yeah.
definitely give you the maybe the code to doing this. Yeah, and the answer is yes, AI can help you do this. In the old time, like person have to learn what is the simulation and how to write the code, maybe Google the code and write out the code. But now if you have this idea of I want to do this simulation and ask ChatGPT, it will definitely give you the answer. Yeah.
Do any of the participants want to also speak? Please speak to us. Let us know what you think. Yeah, do any of the participants want to say something?
So I'm seeing that extraterrestrial intelligence, this AI. I think there's workshop in America, maybe some other places is talking about use machine learning method to find signals, pattern
Yeah.
outside the space, and I think a lot of people are doing this right now.
Mhm. Yeah.
No, there is people in around the world try to use SKA data want to find out some signals. Yeah.
Yeah, anyone wants to say something, please. Answer you want to answer.
That is exactly what Shashan was commenting, that we're supposed to learn to use AIs. It's not, don't take the answer of an AI, or sorry, of a chatbot, as gold. You're supposed to read the answer, understand the answer, see what the answer is about, and then eventually accept the answer or not, but learn to use the AI.
Yeah, I think it's a lot easier for all our this generation to doing this because we grow up without AI, without the ChatGPT, and we have already learned a lot of things before this. What really concerns people is the next generation. They grow up with AI, and they might not have the ability to talk to tell the difference, to tell the right or wrong with their own knowledge. So it's really important to keep learning yourself, but not just to rely on AI, but just to chat with it. Yeah.
A lot of the big AIs, thinking about Gemini, Claude, and ChatGPT, I'm sure that they have a study mode. So you can literally ask it to help you learn about the topic. Basically, you ask about the topic, and it will guide you through studying it. And because it's an AI, most of us have lectured or are lecturing. So, but the issue is when you're lecturing, normally you lecture a room of 10, 30, 40, 100 students. An AI with this kind of study mode can adapt to the understanding, to the pace, and also to the interests and the nuances of a specific student. So it's with the help of a lecturer. So it is my serious belief by now is that the lecturer does not need anymore to pass the basic concepts, but the lecturer now is more to help the student understand what can be learned and what is understandable through ChatGPT, through a chatbot. And then the role of the professor goes back 2,300 years to what Plato was calling the demiurgo, which is the maker. So basically, what we have to do now as educators is not anymore to just pass concepts, but to help shape the concepts. Basically, Wikipedia first, and now the chatbots, they allow anyone to reach for the basic concepts. But what we can do now is actually help the people to actually make many steps further. So there's a vast educational potential there. And if someone decides, or if a student decides to take it seriously, the potential is enormous. Sorry about that.
Yeah. See, I have tried it out myself, ChatGPT. You can ask it to tutor you on a topic you want to do, and it does quite a good job. I quite liked it. I was told about, so I explored it. It does a good job. You can ask it to tutor you and do things like that.
But there are certain issues like sometimes when you ask a question, it collects information and puts it through, and you don't know where it's picking up that matter from. It could be right or wrong. See, as long as it was Google we knew when we searched. It got us to papers and we exactly knew who had written it and which of, they are coming from a proper organization, proper university or not. But these chatbots can pick up any information linked to that topic and put it forth. So one has to be extremely careful. So some very specific issues from pure mathematics, when I tried to ask these bots, they were absolutely wrong. They were, far from being anywhere close to it. So one has to be very careful. Many a times they are right, many a times things are good, but one has to be extremely careful how we use it.
There's an exercise that I have been doing a couple of times that is to ask to use the same prompt in different chatbots, and often it's very interesting to see the responses. And I'm not sure if it's politically correct to mention it here, but I'll do it anyway. So my experience is ChatGPT and Claude are significantly better for information exchange, for discussion, and depending on the model that one uses within these two chatbots, they actually tell you what are where they're taking the information from. They give you the link and you can click on the link and check the link, and it works well. My experience with Gemini instead is that it's very good when I ask it, tell me information about this topic, because Gemini is Google, right? And you cannot see my t-shirt. Gemini is Google, and so basically has access to a lot of things, and normally is very good at receiving the information and summarizing for you. But if you ask Gemini, give me, I'm writing about this topic and I have this text written, so now help me, but I'm not inspired to write a title. So help me writing 10 different versions of this title and help me writing 3 different versions of the abstract. It will fail me. It has always failed miserably with me. Whereas the other chatbots work very, very well. So my long story short, OpenAI and ChatGPT and Claude, I find them very good as research partners, and in the sense of brainstorming, writing body, perfect. Gemini, I find it much better as a Google extension. Like, go search the internet, get back with useful information, and it normally does a good job. Returns the link. I think this is its sources. I think that is the most interesting bit, because then one can go and check if the information was correct. It's basically you can think about it like a Google 2.0.
Yeah, it was that's why we have to learn, and we have to understand different chat. It reminds me a joke when all this ChatGPT come out, and it's like I promote myself to a team leader, and all ChatGPT, DeepSeek, Claude is my team member, and I assign different works to them, and they give me the result. But finally, I have to come out my own decisions as the team leader.
I love it.
Yeah. I think there's some questions. Maybe we, Priya, do you want?
Yes, so
Yes, of course. As you mentioned in the discussion, the large volume of data is being generated every second in this field. Do you think this creates significant career opportunities for data scientists, particularly in working with astronomical data?
I think it works the other way, in the sense a lot of astronomers are becoming data scientists because, in terms of job opportunities and things like that. So, the reverse movement is happening more compared to data scientists becoming astronomers. I think more astronomers are becoming data scientists. I think that's the same everywhere else, right? What would you say?
Yeah, that's because there's more money if you apply that to market and so on, rather than astronomy. You're applying to astronomy is doing it for your pleasure, and they're not many routine, returns. So in fact, we are consciously teaching our research scholars to take up problems where they can use AI and ML in that, because they'll develop those skills. And yeah, secondly, the jobs in pure sciences all around the world, they are less, while the market is big and open. So they have more opportunity of getting jobs and a livelihood if they apply those techniques elsewhere. So we are encouraging our students to learn and use these techniques because it opens up a whole big window for them for getting jobs in banks or in big companies, organizations, and say Google or Amazon, or which are very well paid jobs. The other way around, like Priya said, is less. Those who are already in the industry, rarely they would come back. There are cases, but there are those who are really dedicated, really interested in sciences or astronomy, who come the other way. And otherwise, the flow is out from academics and more into the industry.
Yeah, any comments from the others?
See, in India, the general trend is there's a lot of peer pressure from their peers and their parents, where right after their 10th standard, they get billed either mathematical sciences, biological sciences, or others. And mathematical sciences, they want to do engineering because that gets them jobs right at the age of 23, 24. While those who go into research, even till 31, 32, you are not sure whether you will get a permanent job or not. And people from life sciences, they would prefer to go into medicine. So those in sciences either go into engineering or medicine. There are very few who are genuinely interested and who can fight their peer pressure, and they have understanding parents who are allowed to proceed ahead. But mostly it doesn't happen. So many of them are pushed into careers in engineering where they are generally not very happy, but they are earning money. And so hence that creates a whole big problem. The number of jobs also for academicians are less, and you have to be very lucky to be getting a university position or in an academic institution. So I think it's the same in other places where engineers earn more, they settle down much earlier in life. While in academics, it's a difficult path all through. It's fun, yeah. When once you have chosen it, you and me, we know that we really like it. We have done it because. But for most others, they are forced into engineering or medicine.
Alessandro writes, in my view, number one, we should include what is AI in academia. Yes, definitely. It would help understand how to use it. And two, no AI-based tests, pen and paper kind are needed. Yeah, absolutely, that's true. Yeah, they actually so much of overhype about it. Either AI is our friend or it's our enemy. We have to decide one of the two. You know, it's definitely not that, but they make it seem like that. And yeah, I would agree to that. What would the others say? Please, this discussion is even open to participants. If somebody wants to talk, please, this is your time to speak. Last one.
Participants, they're very quiet.
Yes.
I think everyone's tired. Been a long day.
Yeah. Actually, for them also it's 6 o'clock now in the evening. 5:36. Yeah. Should we wind up our file or? Yeah. So I hope all the participants have entered their details on the chat thing so that the certificates can be organized. Because in this way, we actually have track of people who attended. That's why we've requested you to put it in your chat, in the chat thing. So I guess I saw a lot of names, so I think that has been put. So I wind it up.
Yeah, we can create a GitHub or some where we can put all the resources and material. And maybe we can take a few days off so that we compile it in a proper way and put them up together. And if you all agree, we can have more sessions rather than having one day with so many things in it. This was just to tease them, had go at a lower pace uh, and Alexander did a very good job with uh, Vizier and Symbol. This is very well done. And it would be of great help for people if they can be made to do, they query as you teach them and go on. So we'll need to extend it over a longer period. Every weekend, every Saturday, or on some particular day.
Yeah.
Sunday or Saturday or Thursday, whatever suits all.
So thanks, we have some good feedback. So we will be sending you all feedback forms. It will be really good for us if you all, replies, that we know how was this whole thing taken. And thank you very much for attending. I can see that there are a lot of Indian students also over here, and I'm sure all the others, because of the time difference, this is probably, difficult for many all who are attending. So thank you so much for attending. And if you're fine, we'll wind up, right? I heard there's a cocktail party for the LOC, which we miss. We're too far away. So anyway, so thank you so much, and let's keep in touch. You have our emails, and let's keep in touch. And yeah, so we have some nice feedback from people. From Bruna, I'd like to extend my sincere thanks to everyone for today's session. It was an incredibly valuable opportunity. And I hope you are all aware that the whole thing has been recorded and it was live streamed onto YouTube. So it's available on YouTube. So please go to the BRICS Astronomy channel, YouTube channel, and you'll see recordings of all this, as well as the other activities we've been doing as part of the BRICS network. You'll find it on that location. Yeah. So thank you very much, and we'll wind up. So bye-bye. Thank you, and see you sometime next time. Bye-bye.